Okay, welcome to the third session of this first round. I don't see Joe connected, so I'm just going to start because it's getting late for me at least. So today we're going to talk about underlying event and Pileup, two kind of important concepts and observations in hadron collider physics. So I originally wanted to address this mostly in the context of the jet measurement, but when I prepared the slides, I changed my mind a little bit, and I will maybe tell you a little bit more about underlying event and Pileup in general. And I have some hope that we're getting actually to a detector part today, because that's kind of the interesting part of what we have to deal with at the LHC in Atlas. Okay, so I don't know why my screen is so slow. Oh, there it is. Okay, so yesterday we talked a little bit about jets and calorimeters mostly. The title was Jets and Detectors, but clearly the focus was on calorimeter. We talked about the principally complex response for jets due to the mixture of particle types and the combination of a linear electromagnetic and a nonlinear hadronic response with a relative signal yield increasing with jet energy. We talked about more important effects on the jet reconstruction, which are related to the acceptance, the visibility of particles in the detector, in particular in the calorimeter, the effects of the magnetic field, that material, all these little things we mentioned, and also limitations, in particular in the measurements of hadrons, which are related to leakage at the back of the device. I showed you at the end different jet images coming from the different ways of defining the calorimeter signal. That will be something we have to get back to next week when we talk about Atlas-specific signals and go a little further on that stuff. So today we talk about the underlying event, and this is actually a snapshot from a video that is posted on the internet that shows vacuum fluctuations on a lattice, and Peter Scans, from whom I stole this image, put on top an event, and he put a big question mark in parts of the event structure, which is mostly related to hadronization. So the effects that come from the parton shower, and we see as lots of particles. So we had a little bit of this discussion already, but let's review quickly what the hadronic final state in theory really is. So we have the hard interaction, of course, a matrix element that can be calculated with perturbative QCD to a fixed order. Most processes can now at least be calculated to NLO, some of to NNLO in powers of alpha S. So we have gotten quite far. Then we have the parton shower, which is characterized by soft collinear logarithms. There were significant advances in calculations in the context of jet substructure analysis, where Sudakov-like suppression was introduced in the resummation of these logarithms. And the first reference to that I found was at Boost 2013. That was in the context of actually calculating the jet mass. The matching is one of the issues that we haven't talked about yet, but this is in all models, you have to match the hard scatter partons with the parton shower. Typically, we call these kind of generators a matrix element where the hard interaction is calculated and the partons come from, and PS, so maps, this is then the parton shower. There's also code available to actually match the matrix element with next to leading order parton shower, which is an interesting but not yet often used concept. So then we have the hadronizations, where some power corrections have been developed in infrared safe regimes, but there's a lot of phase space which cannot be calculated. And the underlying event, which there are a few attempts to start calculating these things, but it's non-perturbative long distance QCD. So, and it's still very divergent at low transverse momentum. So we are not very far with that yet. It has some perturbative hardware interactions which can be calculated, but in general we have to model it using the data. So if you look into what is actually out of this is a possible underlying event contribution, it's a little bit a matter of taste, if you want. The particles of the hello.
Sorry, my mic was on. Sorry.
Okay. So the particles from the hard scatter process can be part of the underlying event if they are hard emissions in the context of initial or final state variation, or part of the multi-parton interactions. These are sometimes resolved in individual jets. This is, of course, what we like. Then we have a better handle on the final state. But often these emissions, while hard, are below threshold for jet finders. So we still have a more inclusive or integrated picture of what is going on in that part of the phase space. The hadronization, it's the final state particle production by mostly soft emissions. It can be close to the hard energy flow. So it can mix in with actually the jet that comes from a parton while not being actually related to this. This is a question of, which is an unresolved question of basically what they call color reconnections, meaning do the gluons see each other and talk to each other, even though they come from different vertices inside the collision. Then we have the soft multi-parton interactions, the beam remnants. They are often not used or often not needed much for modeling a final state, but they can play a role if we believe in color reconnections. They certainly play a role in events where the central particles are color singlets. So we should model them as best as we can. There's a list of non-perturbative phenomena that Peter Scans once sent me, and some of these things are not really considered. In principle, there can be in the parton shower, there can be annihilation from more identical particles following Bose-Einstein correlations, and that can yield new particles. I don't think any of this is actually modeled. Color reconnections are not modeled, but they are parameterized. So there is a range parameter, which is part of the tuning. And there are other connection effects, which I really don't hear much about, and I think they're not that important, but at least from theory and phenomenology, thinking about these things. So if you talk about soft physics tuning, the big starting point is that we assume that the actual fragmentation process that gives us the jets and that in the end is independent of the collision environment. We assume this because we don't really have the tools yet to, or will probably never have, the tools to tune, for example, the flavor production in the parton shower in the fragmentation functions using LHC data. But we have very, very clean data from lab, which is still used to tune the right amount of flavor quarks and particles being produced. Also for the final state radiation and hadronization, we have very clean data from lab, but we are now doing combined parton shower on multi-parton interaction tuning using LHC data as well, which this is taken care of. For ISR and the primordial KT, which is the intrinsic KT of the collision, so I think it used to be Fermi KT, used to be called Fermi KT. For this, we can use LHC data, mostly jet shapes, dijet decorrelations, longitudinal jet fragmentation using tracks. So we have some handles that are sensitive to these parameters in the soft modeling, and we can tune them accordingly. So for the tuning of the multi-parton interactions, we have a variety of final states, and relatively recently we even included things like TT bar, production. Usually you use dijets, just QCD production. But when you want to combine the MPI tuning with the Pardon shower tuning, TT bar is one of the nice final states you can use. And there were recent talks from Atlas about that. I have not really found anything in the shortage of time. So here's the result of a tuning from lab, which we actually redid in the old days in Atlas. We retuned, we reran all the lab tunings together with the few tuned parameters for which we could use LHC data. And you see here how well we can tune to these productions compared to the lab and SLD data. Now there is a sensitivity to your choice of parton density function. This is very typical. So the tune, when you specify a tune, you always have to say which PDF you have used. There's basically no way around it. The tunes are not valid out of that context in most cases. So then we, in case of the lab tuning, we used even, we looked inside jets. So we looked at the splitting scale. We used the splitting scale inside jets to tune final state radiation and hadronization. This makes a lot of sense because the splitting scale is one branching inside the jet. Clearly, you have to use a KT jet finder for that because the cluster sequence need to have a physically meaningful order. And here you see the splitting for the next to last and the next to last branching. Those scales have been measured in lab and by Aleph SRC and then tuned to the Pythia has been tuned to those. In the early days of LHC, we tried ISR and primordial KT tuning. Here you see very, very early results on the left using Atlas tunes. Now, when I say tuning, the only generator we can really tune is Pythia. Herwig, Sherpa, typically author tuned. So we don't really have the setup to tune those. So mostly we tune Pythia, and what you see here is actually Pythia 6. So it was really the early days of LHC. But you see how well we're able to measure, to tune the Pythia to the jet shape using phenomenological parameters. This is a particular, this tune is called Perugia. This was a tune that Peter Scans helped us with. Then we, on the right, you see a tune that we did ourselves with the Atlas data. We've tried several different tuning models and several different PDFs. And you see that we can get really, really good agreement on the jet shape once we use the LHC data. So in a more modern setup, probably since 2014, 2015, we tend to use everything together in just one go, if you want, because we now have very powerful software to do this. The package is called Professor, which is a multidimensional, basically it's a multidimensional minimizer that that adjusts the parameters according to the experimental results. So in the tune, the most recent tune I could find for Pythia 8 involves the cutoff for the regularization of the QCD cross-section at very low PT. This goes down as 1 over PT to the 4th, and it's an infinity at very small angles and very low emissions. So there's a regularization parameter PT0 that is put in, which itself is parameterized in terms of two other parameters, which is the reference T0 and an exponent to the ratio of the center of mass energy over the reference center of mass energy. For historic reasons, this is still the teraton energy. So in addition, because MPI are other partons and the one that actually goes in the hard scattering, you need a matter profile, you need a distribution of partons inside the proton, and the formula that is used for that, you can see here. It used to be a double Gaussian. This has been replaced by this formula for pith 8. And the formula depends on the distance from the thrust axis and the momentum fraction that the gluon or that the parton is carrying. This has three parameters, actually a function. I could not find much documentation about A3, but what this function really looks like. So I know it's tuned, but I couldn't really find out what is tuned inside. But for the function in the exponent, there are two parameters that are tuned when we do this. You also tune the reconnection range, which has a value between 1 and 10 typically. In some tunes, we allow it to be 0. That means we have no color reconnection. This is also a free parameter in the tuning. Again, all this is phenomenological. We don't really have better theory guidance than that. We have a naive expectation, which is that the multi-parton interactions are the same in the underlying event of a hard interaction and the minimum bias event. We assume that the parton showers are universal with that respect, because we don't really have a good handle on tuning parton showers in soft interaction and minimum bias events. So we need to model those. We just need to do the use the tuning we have from the hard scattered interactions. We have no really jet structures and minimum bias that are reliable or statistically significant to tune to. It's actually not quite true. And it's probably one of the reasons why we, for years, did two different tunes. We tuned the underlying event separately from what we call minimum bias tuning. So that is just the tuning of a general soft. Since our recent tune A14, we now tune those together. We call it a global tune. There are some stresses in the distribution, so this is by far not perfect, but it seems to be sufficient for most physics we do, and it seems to give us the right impression on the underlying event as far as we are sensitive to it. So I cannot talk about underlying event without mentioning Rickfield. So this is a very classic approach on how you actually find regions that you can tune to, energy flows that you can tune to, which are not affected by the hard scattering, and so are very good handles on the MPIs. So he started to look into the transverse region of dijet systems. So he looked for very clean back-to-back jet activities and defined these two transverse regions sketched in the little drawing. And actually in later developments, he defined one min and one max of those. So one with more activity than the other, and tuned those separately. Here within these transverse regions, you can measure flow observables like PT flow or number of charge tracks, average charge track transverse momentum, average of sum of charge track transverse momentum, and so forth, and the correlation and the RMSs, the spread of those as function of for example, a leading jet in the towered region, or you can also use a leading track, which is often more popular than using jets. This is a standard in MPI tuning. We still use these regions, and this is certainly in the history books forever. So here's an example where we use the dijet azimuthal decorrelation to tune several PDFs and several tuning models, including Peter Scan's Monash model. And you see here that in this distribution, we actually tune to the right part of the distribution and not so much to what is left of it. So the reason for it is if you have a very clean sensitive back-to-back scenario, which is to the right, we're getting more and more confident that we have a 2-to-2 process, a clean process in the transverse regions. If you go too far, if the two jets get too close together, and too far away from back-to-back, there's certainly an influence from a third hard emission coming from a hard process. And in the case of the modeling, having been calculated by the matrix element, which is now available at NLO. So we may actually confuse things here, while it's a fairly clean scenario when we stay away from regions where significant jet production is very unlikely. Okay, so let's move to the next soft contribution to our final state. The famous Pileup, which are additional proton-proton collisions in the same bunch. They're clearly introduced by the high proton beam intensities, 10 to the 11 protons per bunch or something like this, and the large inclusive proton-proton collision cross-section. What this means is that per crossing, we have much more than one collision. And you see in this little graph on the left how this developed throughout the years. So in run 2, in the early days of run 2, we had about 13 additional collisions in the beginning. Usually the convention is that the average mu names the number of additional conditions. So it is 0 for no pileup. But there are also different interpretations of that. I've seen that in papers. It used to be like that, like I said. So let's assume that's it. And you also see that we're getting a little higher in pileup, but also the shape of the distribution changes because the beam intensities change throughout the run year. So this is a number we have to put into a conditions database. We have to remember what the average mu profile was if we select a sample from the data and we want to match Monte Carlo to it. On the right, you see a very old plot with very simple, actually was a very detailed simulation of the end cap and forward calorimeters of Atlas, but no simulation in the central region. So the final state here is a VBF, vector boson fusion final state, simulated with Pythia 6. And the most interest I had those days was to try to figure out how Pileup changes my picture of jets and other energies going in the forward direction. So you see clearly 2 jets, very nice, and you see a little bit of extra activity. There's some little green dots around there where other particles enter that region. And if you add the Pileup, this is done in not exactly the way we're doing it now. This was a simpler approach, which we actually may go back to now. So if you add the Pileup, you see that the jets are still there. This is for sure, but the shape has changed considerably, and this may affect your measurement if you really are sensitive to anything that happens inside the jet, or if you have any other plans to use these jets. There is a change in amplitude as well. If you draw a fixed circle around this, unfortunately, I lost the numbers. I cannot really do those, but the PT of the jet changes as well. You also see that there's a lot of activity scattered into the calorimeter away from the jet, which is pure Pileup now. And if you look very careful, you see here negative entries. So this is of course, we don't have negative transverse momenta. So this is a feature of the readout of the calorimeter, which I was hoping we come to today, but I see already that won't happen. So we have to talk about this another time, or you have to read it up yourself from the slides. So as for underlying event, we need to model our Pileup. And this is a job that is not quite as easy. So what we usually do is when we want to have a full simulated event of a collision in Atlas, of a bunch crossing in Atlas, we overlay the hard scatter finite state with minimum bias simulations where we just add as many simulations as needed to get to the number of collisions per bunch crossing of the period we're interested in. These overlays Poisson distributed, so it's not always the same number of minimum bias events overlaid. And the average overlay, the average number follows the profile that is given in this little plot for 2018 data. So we sample from this profile to match and then smear the sampled number by Poisson to get the number of actual overlays. The quality of the modeling for minimum bias is certainly not perfect. The phenomenological models are quite stressed. It actually turns out it's very hard to tune multiplicity of charge tracks and the average PT with the same to data with the same high quality. It's the models usually don't allow that. They reach boundaries of the parameter space where they can't move anymore. So we used to focus on getting the PT right, the energy, so to say, right. And not so much the multiplicity. If you really want to, reconstruct a signal in the simulation, including all the pileup, our calorimeters readouts requires you to take about 625 randomly sampled and fully simulated minimum bias events to add to your signal event 625 bunch crossings, I should say. To really model the effect of pileup in the Atlas calorimeters. We did this in the very beginning. This is just we cannot continue. We couldn't continue like this when we started to generate billions of fully simulated events. So the idea would be ideally you have no period in these randomly sampled events. So you have an infinite period, so that every event is different, but you cannot have such. So we use a slightly simplified approaches, looking a little more closer to what is really the important part of that contributes to pileup around the signal peak and so forth. So this has changed throughout the years a little bit. We have also taken actual data to model the final soft state in the hard interactions, hard interaction generation, hard interaction Monte Carlos. So the advantage of that is we're taking in the data taking, we're taking what's called zero bias events. Those are events that are randomly triggered. Typically, we implement rules like 10 turns after the last hard electron trigger. So we just read the event no matter what it has, no matter how much energy flow it has, how many tracks, it doesn't matter, it's just read and stored. And so these random events give us basically a good picture of an empty detector with all the effects of pileup still in the signals of these events. So we don't really have to use 600 plus events to overlay to get the right pileup. In the calorimeter, we have just one event to overlay, but it requires significant computer sources, and there are some other problems. In particular, of course, when you take real data, this is connected with conditions of the detector and of the beam and of the readout. So you have to kind of make sure that if you want to overlay real data to your final state, that your analysis restricts itself to the period that these conditions cover. And that is technically a big challenge. So we have done this only very selective so far. We also need a little bit more data than usual to do this overlay, because we used to do it in what is called the digi format. This is the raw signal, the raw digital signal coming out of the detector. We are now going back to what I did for my very old pileup studies, which is we try to overlay just the energy, the reconstructed energy, cell by cell, and see if this gives us a realistic description. The plots below, it shows how much problems we have with the generated pileup and how well zero bias overlay can work. So on the left, you see a distribution of the cluster transverse momentum in the forward region of the Atlas experiment, 3.8 to 4.0. This is a very inclusive distribution. So we just take all the little calorimeter clusters, which are just a group of cells, connected group of cells, and measure the PT, and we put them in this plot. And if you model this, you see that the yellow distribution from the already tuned Pythia Monte Carlo does not really represent the shape very well. And if you just take the same generated final state, which is just the Z production with 2 muons as a decay product, if you do this overlay with the data, you see that you can get the shape of the distribution very well, actually. So the data, the minimal or zero bias data, covers the correct, provides the correct image of Pileup in the detector, also in this rather complex forward region. So we did a few studies along these lines, but it's not used generally in analysis because the overhead is enormous in terms of computing. I think there's some revival of the effort going on, but I haven't heard recently. So some features of the Pileup we should keep in mind. So if you have a large number of collisions per bunch crossing, these individual Pileup collisions are actually statistically completely independent. So if you overlay all those, what you basically get is a diffuse emission of particles across the event plane. But there is a common feature to it, which is there's a rapidity dependence of the particle density, the numerical particle number density, and the particle PT density. And the 2 plots on the right shows us for Pythia 8, simulating Pythia 8 minimum bias. This tune 4C is actually came from CMS. I think Rickfield did it in the early days. We used it for a long time for forming bias. So you see here how the PT of the particles drops towards forward and backward, and how the number of the particles drops. So this rapidity dependence is not terribly important, except if you want to do what we talk about next, which is a correction for the Pileup. You have to keep this in mind. Also, what it means is if you have a diffuse emission of particles all across the event plane, you get those are scattered into your jets. There's unavoidable contributions. The particle flow from Pileup has nothing to do with the hard scatter interaction. There's no connection imaginable. The actual amount of energy that is added into the jet depends on the activity of the Pileup in the event you have read out. So we have to do something about it. We cannot model it well. The Pileup conditions are not always known that well. So we developed a system where we use the data itself to tell us how much Pileup we should subtract. Actually, when I say we, that is not correct. This came from our good friends Matteo, Gavin, and Gregory. So they thought about what actually Pileup is in terms of what it actually contributes to the event. And one of the things they thought about is, so if you have a large number of particles scattered into your event plane, you can probably the transverse momentum density in this plane gives you some handle on Pileup. Now this plane also contains your hard scatter. So, but imagine you can measure for each 4 vector in the plane, you can measure a density, that's the PT over some area, and you then take the medium of the distribution in one given event. You take the medium of the distribution, which is basically not affected by any hard scatter in this plane. So you really catch all soft stuff that you either see or have modeled. you have a good measure of the Pileup activity, and they have shown this, we have seen this in the experiment. The big problem is that, of course, a particle form momentum does not have an area concept with it. It simply doesn't have it. So we either come up with a model, like I think yesterday we already mentioned that, Voronoi or ghosted areas, but those are all more or less stochastic models, which may not be the best at the level of individual particles. But what we can do is we can collect all these particles into jets. And then we have a relatively reproducible catchment area measurement, because now we have a bundle of 4 vectors. So you remember probably the figures I showed yesterday about the jet areas from the different jet algorithms. So the plan is, or what we do, it's not only the plan, we actually do this. For each event, we cluster the whole final state with a KT or Cambridge-Aachen flavored KT algorithm to form small jets that have a catchment area attached. And we do not apply any PT cut to these jets, so there's no threshold. In principle, we can use anti-KT, but when we started doing this, we always thought anti-KT stamps out a circle out of the event plane in terms of catchment area. So the further you go down, the softer you get, the funnier the areas look, because some areas are already taken by a harder jet. And that gives a bias in the density measurement. So and it also has the potential to leave more voids between jets. So we prefer the dynamic areas that KT and Cambridge-Aachen give us. In addition to these jets, all of which have to have some finite PT, because it's impossible to cluster anything around PT0, we try to get a number for jets that actually have PT0 and try to just get an estimate of how many of these jets would be in the event. So the way this is done is by assuming that there's a nominal area for empty jets, which is not pi r squared. It's well explained in the paper that is linked on the right side of the slide. So it's a certain fraction of pi r squared, and what you do is all the all the void areas in the event plane, you sum up, you calculate the area, total area, and you divide by the area of the empty jet. So you count how many empty jet areas I can get into the open area. This can technically be, it does not need to be an integer number. But if you put this into a distribution, then the median pulls towards 0. So there are a contribution to the event density rho event. So it's part of the concept, and it's the way we do things. And I kind of like it because it combines the occupancy with the actual PT flow of the soft final state. So this makes a lot of sense to me. Once you have this rho event, which you calculate for each event, and if you think about it, it's also independent of, it's somewhat independent of modeling, because Monte Carlo will give you a certain rho event and data will give you a certain rho event, but they don't have to have the same underlying models in terms of soft emissions. As long as this rho event is a good measure of soft emissions in general, we are good. There are some problems with this ansatz because of the way we do jet calibration atlas. I will come back to this next week. Anyway, you take your original PT of the jet, you subtract the area of the jet times the density, and you get a corrected PT. And then you ask, is this corrected PT above the analysis threshold I want to apply to my jets? So you lose a few jets, which probably are good candidates for being from Pileup. The nice thing about this is technically you don't have to cluster your hard scatter jets with exactly the same the soft jets for the rho event measurement. That's really not needed. But the method on how the area is determined should be the same ideally. So if you decided to go for ghosted area or Voronoi, it should be consistent. Even though I don't remember any big discrepancies, but I think the general attitude is that it should be consistent. Okay, so the last thing for today then, so I will not get to my nice detector stuff, is the question of, can we separate the pileup from the underlying event? Well, that is basically impossible. So the phase space that both the particle flow from both sources cover is absolutely overlapping. It's the same mechanics. It's all soft collision physics. They have the same driving things. Pileup has a factor applied to it in that it's, I think you have about 2 or 3 MPIs, and you have up to 60 or so pileup collisions. So, but there's certainly no particular way, no good way, if you don't have recognized structures like jets from the underlying event, to actually identify contributions from the underlying event. Both are also largely uncorrelated with the hard scatter, except in case of the underlying event, if you believe the color reconnection model, like the one implemented in Pythia, and you believe the tuned color reconnection range is meaningful, then if you get close to the, typically if you get close to the hard scatter, there is some correlation of the underlying event activity with the hard scatter. So underlying event is a little bit different from that, but again, these things are at the 500 MeV GeV range, and they really are wildly overlapping. So it's very hard to say anything about. When you apply this famous jet area-based pileup subtraction, you unavoidably take out underlying event from the jet. It's in there, and you take it out. We tried at some Lezouche workshop years ago to measure, or to find a measurement that tells us how much of the underlying event we took. That is pretty easy and assign them and do that, but in the detector, I really don't see any way of doing this. There's, as with all of these methods, after the jet area's subtraction of pileup, based subtraction of pileup, you have some finite pileup survive. You have lost some of the underlying event or all of it. So the problem of this particular method is really that the transverse momentum density we use reflects the event-to-event fluctuations in pileup, but it's not sensitive to any local fluctuations in a given event. For example, what happens very near jet. So what are we going to do about the underlying event when we don't really know how much we took out? Well, we came up with a very simple concept. At LHG, we calibrate our jets including an underlying event, which is modeled in the context of our nominal generator that we use, physics generator that we use to do the Monte Carlo part of the calibration anyway. And next time we talk about what that is. So the tuning of the underlying event to experimental data is essential to get a somewhat realistic picture of that. If there are underlying event effects on jets, which are typically more significant at low PT jets than anywhere else, and they have an effect on spectra or on anything else you do in your measurement, you may have to unfold those using Monte Carlo techniques. Then we had this glorious idea: we have data without pileup, so can we use raw event to measure the underlying event just in a clean collision? Well, the problem with that is that the particle flow from underlying event is actually quite sparse. So it's not as dense as 60 pileup events. So we have a very low occupancy in the detector, which means we have a lot of PT0 jets. We have a median of 0 most of the time. We can redefine this. We could go to an average. We could go to a limited acceptance, that's this eta slice, or rapidity slice. But we have not followed up on this idea. But we have no pileup data, and maybe it's interesting to look into this. I think I have used my 45 minutes, so I will stop here. Even though I find the next part much more interesting, but I knew it would be too much. So, any questions?
Yes, can you hear me?
Yes, I hear you.
Is the underlying event really uncorrelated with hard scatter? Because maybe you can reconstruct the primary vertex and see that the underlying event comes from the same primary vertex?
Well, the underlying event, I mean, the collisions are, happen inside two protons. So you have a distance scale of typically one Fermi, right? 1 femtometer. So there's no way in the world that you get a second vertex from an underlying event.
No, I mean maybe we could say that a small PT jet would be an underlying event because it would come from the same primary vertex as a very high PT jet.
It can be, but it can also be hard radiation on the final state, on the hard final state.
Okay.
Which we usually don't consider underlying event. If we can resolve it, actually get a jet, even a low PT jet. But I think I now understand what you mean. And I think we have tried this. For example, what you could do is just look at track-based jets, which don't need to have 20 GVPT. You can have a few GVPT. And you have a very clean vertex assignment. So you could look at track jet activity around a hard jet. I don't know if anybody has followed up on this and if you have enough information. Track jets at this low PT usually have only a very small number of tracks. So I think it's certainly non-trivial to associate those with the underlying event. There are analyses going on where we explicitly use we require a final state radiation, a jet from final state radiation. So those are kinematically a little bit decorrelated from the rest of the final state. So people have developed techniques to identify those. But underlying event is really hard to directly measure at LHC.
Thanks. Okay, I have another question. I don't know.
Sure,
if,
go ahead.
If you can quickly recall just the acronyms FSR, ISR, and MPI and PS.
Okay, so FSR is final state radiation.
Okay.
That's the radiation of a final state parton. ISR is the initial state radiation. That's gluon emissions typically of the initial parton going into the hard interaction. Then we have the MPI, that is the multi-parton interactions. Those are the collisions that happen in the same two protons by other partons, except the one you're interested in. And PS is parton shower.
Okay, thank you.
The whole thing. Okay. Any other questions? Okay, so I apologize. Yesterday I posted the slides a little late. Today it will also be a little later because I have 2 or 3 other commitments due tonight. And I already saw a few things I want to fix. So they may show up only tomorrow, which is tomorrow in Europe. So you have a chance when tomorrow morning you should have some. Anyway, if there are no more questions, then
I actually had a question.
Yeah, go ahead.
So I know you said this a few times, but it's never been clear to me. Why do pileup and underlying events show basically the same PT pattern?
Well, with some respect, they're the same mechanism, right? You have low Q-square parton collisions. I mean, every pileup, if you really think about it, every pileup collision has some kind of underlying event itself. But the most likely collision that will happen is a very low Q-square change, and that's very soft. And that is what also happens in the multi-parton collisions. The only difference is that if you believe color reconnection, it may be that the collision products of the MPIs talk to the hard scatter. They see the hard scatter. But I'm not sure that we have strong experimental evidence to this, but it has been implemented in Pythia for a long time. and we use it in the tuning. So I have to find out if there's any experimental evidence.
Okay, thank you. I see.
Any more questions? Okay, so that was the first week. Sorry for any technical problems or unclear slides and stuff, but I try to improve. So we can start over again next week when we start to talk about Jets and Atlas and the calibration of Jets and Atlas. And I will probably start with the online pileup suppression strategy that we've implemented for the Atlas calorimeters, because this is kind of a fascinating topic. So I will take a little bit of time out of the jet calibration to show you that. Anyway, thank you very much for listening. And well, you have a recording, so if you have any further questions, you can also send me an email. So talk to you next week then. Bye.